wanted to talk about something that I feel very passionate about. Get your doggies ready, your hot chocolates, your coffee, and we're going to have a talk about evolution. I've been thinking about this theory for the better part of a decade at this point, and I've come to realize a lot of things about evolution now that I really didn't before, because this theory started predicting things about evolution and its very different style. I think it's an amazing theory to learn. I've taught it to literally hundreds of people. I moved to Silicon Valley to pursue it. I've tracked down professors. I've gone to Berkeley and talked to people from CRISPR about it. I've had friends that are neuroscientists and physicists from Ivy League schools. I've come to learn over time how people tend to argue my theory, especially amongst the harder STEM people. They kind of, because I'm coming after a theory like evolution, they tend to be a little defensive at first, oftentimes, and then I keep going and I figure out what they think, and I feel like I always have the answer on how to just change evolution. And it's an amazing theory to learn. People love learning it. They go all kinds of different directions. I wanted to just have this kind of like overall outline of it, because the understanding the theory isn't rocket science, but I know that because this requires a higher level of physics, which is really where I come in, because I've had a deep passion for really inventing physics. I think a lot of guys try to, be like Mike when they're younger. I was trying to be like Einstein secretly. It's a stupid goal, but I did. And I ended up thinking about this certain thing about evolution, and it just didn't make sense to me about just the complexity of it was the major problem here. Like the idea that life is just a little bit too good at doing what it's doing. And I thought of this way to quantify that. We evolved the cardiovascular system, right? If you're a bug, you don't have a cardiovascular system, anything like we have. A cardiovascular system, you can interpret it as this supercharger for oxygen. If you're a big creature, you breathe in, the oxygen gets funneled through your lungs. It gets, the oxygen then is absorbed, pumped through heart, veins, blood. So you need all of these special systems, like a heart, veins, blood, probably a special immune system to handle this. Cells that can handle it, that can make use of oxygen in these different places. So like, let's say you had 6 major systems, just 6. And let's say there was a 1 in a million chance of these systems occurring, because all of these things have to happen at the same time. You can't have a heart without blood. You can't have, you can't have 5 of these things, because you would just die. And, even if you're being super conservative, right, and say like the chance of mutating a heart randomly is, say, 1 in a billion, like a functioning heart, right? Or any of say just 6 things. If you want to say a cardiovascular system's just 6 of these like systems that have to go right, well, that's 6 times 9, which is 54. 10 to the 54 power, because there's 9 zeros on a billion. You multiply, you just add the zeros up, because that would then be the odds. That number is way over the number of creatures that ever lived on Earth, by far. And I know, of course, at this point, like I said, I've taught it to hundreds of people. They'll try to argue. They'll say, hey, it happens slowly. I don't think it really can happen slowly. I just don't think that's the way that it works. And that's really was the true start to this theory. And so I kind of ruminated on that idea and started thinking like, okay, evolution needs a better way to do this. It can't really just be just guessing random things all the time. That all of these complexities that we have, they're too hard. And then you have these other, and then I started looking into things and started sort of realizing there's a lot of things we believe in evolution that just don't make a lot of sense. So how do we solve this problem? How do we end up with something so complex to actually account for life that is scientific and makes sense? And I had this idea. The idea was sort of simple. Maybe life doesn't really need to come from Earth. That, yeah, there's a certain set number of creatures on Earth. I think I've estimated this for the cardiovascular system. Being, again, super conservative is 10 to the 24 when we need to get to 10 to the 54. But the universe is huge. There's more galaxies than grains of sand on the Earth, right? So if life has a way to communicate its genetic information over space, we beat the complexity problem. Because now it isn't about how many creatures evolve on Earth. It's about how many creatures evolve in the universe. Okay. So, and we don't really know how big the universe is, right? If we can say it's at least enormous. You don't want to go like too far down the weeds. We don't know how many dimensions it has. We don't truly know how old it is. I know people will say like, yeah, it's 13.78 billion years, but maybe there's something before that. Maybe our viewpoint of the universe is just this little section in this giant thing, or whatever. Even if that's not true. Life can certainly, by crowdsourcing its information, and even the visible universe, which again is huge, can have major advantages. I thought that out and thought, hell, that makes a lot of sense. Why the heck wouldn't life use a communication system if it's possible? And I think that's where the whole trying to be like Einstein when you're a kid really comes into play here, because I could follow that picture from the physics perspective and started thinking things out. And realized things like how would life communicate its genetic information to, say, a different part of the universe, a different galaxy on a different planet like Earth. And the first thing that comes to mind is, hey, we use electromagnetism to communicate from cell phones and radios and all kinds of things. Maybe we use photons, for instance, and say, okay, so if we're using photons, right, how many photons could travel around the universe? And I did the math on that, and it comes out like using certain assumptions we have to make, like how much life is in the universe. even if you're being very conservative, like let's say 1 out of every 1 billion solar systems has a planet like Earth on it, how many photons is going to hit your body? And the answer is surprisingly high. I estimated that if 1% of your calorie intake from a person was turned into a photon with the range of, or with the nanometers of 250, that would correspond to millions, hundreds of millions of photons hitting every square centimeter of your body every day. The physics concept behind this idea, and this is maybe where like some physicists, depending on how they're thinking about photons, what they think photons are, maybe they think photons are more limited than what I'm picturing. I think that if one photon is picked up, just one, prepared exactly the right way, not absorbed, but collected the right way, that photon could be replicated. And then the characteristics of that photon could, once it is replicated trillions of times over, could create certain patterns. Okay? And what kind of patterns could these photons create? Well, if you know what an electromagnetic wave looks like, maybe you learned in high school, you've got your electric potential sine wave here. Then at the other angle, you have your magnetic potential sine wave following it. And they peak at right angles like this, right? And that's a linearly polarized electromagnetic wave, what you're used to seeing. A circularly polarized wave is the same thing, except it twists over, okay? What does that twist form? It forms a double helix. It forms DNA. And that is a major clue right there. We finally have this explanation why a DNA helix even exists. It's a very specific shape, right? And it just so happens that it's the wave function of a photon. And have you ever heard that, right? Have you ever nobody makes that connection, right? Because they're not thinking about what does DNA have to do with electromagnetism. Most people probably are not even aware of that. I've even, like I said, I've talked to professors from CRISPR, right? That's the gene editing, their gene editing mechanism. And, ask them if they're aware of that. And, no, because there's no explanation for that, right? Life could, if DNA really is just this memory card, it could be any shape. It doesn't have to be this twisty ladder. It could be a triple helix. It doesn't have to be a helix at all. It could be anything. But life uses these helixes. And that's a major clue here. Right there. So let's say if life captured just one of these photons, captured it, replicated it, it could fire off trillions of these things, and it could then trace out this helix. Now, maybe this photon that it got has certain characteristics of where it came from. Maybe a T-Rex on this planet just has this shape, and then 2 other T-Rexes on this other planet across the universe have sex. They mix their DNA, and then the DNA just sees if it resonates with just the right shape. And we don't need to really get into these details too much because it kind of derails it. But what can happen here is, just by chance, has the right shape. It simply says what other waves, what other photons actually can resonate with this certain shape, and then it can be reasonably sure that it's a real life organism that's going to be successful. And then you have the whole detailed instructions on how to build a life form so that the mother doesn't have to figure out, like, hey, how do we physically engineer something based off a male and a female? Just to look at a person, just every tendon, every vessel, like, just the physical engineering plan of life is so extreme that you just avoid that whole problem right there. Life doesn't improvise, right? What I'm saying here is that there's other me's in the universe. There's other Chaunceys, and I guess she's a poodle and a Pomeranian mixed. Like that doesn't really make a whole lot of sense. But if you mix it, hey, you're going to find something. And whatever that something is going to be a real life creature. So you avoided that problem of a poodle mom or dad mixing with a Pomeranian, having to figure out how to engineer this little badass. That's a major clue. The next thing you could say is, how do we create these photons? Are you hiding, Chauncey? She's a little shy. How do you power them? When we're answering these things, as like with most of the things that I bring up, I'm bringing up things that don't make sense, right? They're ubiquitous to all life, and they fit into this electromagnetic plans. Okay, so what power source exists in all life, all cells, that maybe doesn't make a whole lot of sense? And I learned this in physiology. We have these things called sodium, potassium ion pumps. And what it is on your cell membrane. hey, I need you. In your cell membrane, your body pumps out these little particles, potassium and sodium, and they pump one out and one in, and it creates this electrical gradient. So there's this electric gradient, which is a difference in electric potential. And this is ultimately energy. And then sometimes these walls open up and it flushes in here. And that's how electromagnetic waves can be formed. That's one way. You can have a changing electric field, which then causes a changing magnetic field and back and forth. Or you can have a changing magnetic field. So in this case, it's your body can create photons right here. And all your cells do this across all life. They maintain this gradient. And it's very energy inefficient. 25% of your calories just every day is just to maintain this energy source. And I was surprised to learn that in physiology, because I thought, like, how could your body, or why would your body need to do this? Why does your body need to be constantly creating this electrical gradient? Why doesn't it just be neutral? It seems like it would make a lot more sense. It seems like just a waste. I think the theory is that it's used for intercellular communication, and I'm thinking there's got to be a lot better way for intercellular communication than to spend 25% of your calories, just flushing in different ions in and out. So like right there, you see your body is placing this major priority on this. And I think that for this theory to be, to work, that makes a hell of a lot of sense, because it's no longer about just how many creatures you create on Earth, because you're not bound to Earth. It's about how much physical signal you can create. Even if you're less successful on Earth, but you create more signal, you can make up for the fact that you have less efficiency. And that becomes a way of answering a lot of questions about when life seems like it's not being as efficient as it could. From a certain perspective, life is being inefficient, but really it's not inefficient, it's maximizing its signaling potential. So it's critical to use those calories. It's just as important, for instance, to create offspring as it would be to, say, create signal. You could use either one, and that becomes a major clue to another. As I was saying, you realize a lot of things that don't make sense about evolution that this theory really answers. Take male and female. Why does male and female dominate the animal kingdom so strongly? From the perspective of Darwinism, it's really wasteful. Half the creatures don't create offspring, right? Why does half the creatures need to be male when we don't even create babies? People would say things like, well, it's because of the advantages of sex. But that really isn't a good answer, because creatures can have sex. They could trade their DNA, and then both of them create offspring. There's snails that can have sex with each other, and then both have offspring. Why isn't this dominant? Like, why aren't fruit flies? Why are there male fruit flies? Why don't they just have sex with each other? There'd be like this equivalency. They don't need to find as many mates, twice as many offspring, exactly as much sexual diversification as normal. You don't have to figure out like different physiology for men and females. It just would make a lot more sense. Like, that's what should be the case if Darwinism was actually correct. But when you look at my theory, which they've dubbed universal evolution, it doesn't make sense, because there's two goals, right? It is just as important to make offspring as it is to make signal. So if you can break these two things apart, have one side focusing on creating more signal, which would presumably be men, and one side focusing more on creating offspring, you can create more as a whole like that. So that is actually optimal. And then that creates this whole new sexual theory, my theory, which we're not going to dig into right now. You know, how do we know that, right? How do we know men create more signal than women? Like, is there evidence for it? What are the tip-offs? And there is this tip-off, and there is this very simple way to figure it out. And there's a way to figure out when it's optimal for your body to create more signal in all kinds of situations. Like, for instance, what if you eat more food? Shouldn't you create more signal? Or, or if the reverse, say you're starving. Or even the way you view the world could change how much signal, like, do you view yourself as being successful, right? So how do you do that? How do you know whether you're creating more signal? And that's where chromosome theory gets into it. With chromosome theory, the way that it works is, so you have these photons. I call them life waves. And what I'm saying is a specific photon carries with it a specific life wave. If you're creating lots and lots of these, depending on where they go, can impart their momentum on specific objects. The 2018 Nobel Prize in Physics was won for optical tweezers, in which case they took lasers, and they shine these little lasers on individual atoms at a time. They could use these optical tweezers to unravel DNA and just move things around. And I think what I'm going to theorize here is that if a life wave could be used to recreate DNA, it could also be used for certain functionings in the body. And this, we're going to talk more about the chromosome. It's more the chromosome that is controlling this process. So you can control the probability of where these photons go by changing the shape or size of the chromosome. So if the body And I've figured out this was always, is from all of the different ways that I've seen this, dozens of different ways, the correlation is very, very simple. If you have a small chromosome, that's a giveaway that your body's creating more signal. And the idea would be like, let's say a bigger chromosome is more energy efficient because it's more thoroughly redirecting all of the life waves to its desired function in the body. Whereas if it's smaller, it's letting it leak out more. So men had your XY, we have physically smaller chromosomes than females do. And that, say, in the mammal kingdom, all males have the XY system versus the females. So that's the major tip-off. So the other thing with that, as I alluded to before, is we can see, say, with telomeres. Here's the thing about telomeres. All right, Chauncey loves telomeres, and I love telomeres too, because telomeres, in my opinion, is one of the strongest supporters of my theory that you can have. And the reason for this is because telomeres get affected by all different kinds of things. For instance, and they get affected in the direction that we could easily figure out by what I've taught about the chromosome. The more your body wants to create more signal, the smaller your chromosome becomes. And that is detrimental to your health, right? So if you have a smaller chromosome, it's absolutely detrimental to your health. Like the majority of the top 10 killers of people are strongly correlated with shrinking chromosomes. And, it begs the question, why this process is happening. So chromosomes, they're the end caps of your DNA, or the end caps of your chromosome. Telomeres are the end caps of your chromosome, and they tend to shrink over your life, but they can grow sometimes. All right, be free, Chauncey. Okay, so if you go on a diet, for instance, how does that impact your chromosomes? You wouldn't want to create as much signal because you're on a diet. You don't have as many calories at your disposal to create a signal, right? So your telomeres would preserve themselves. They would be bigger compared to somebody who eats a lot of food. So for reasons like this, it suddenly makes sense why the correlation across most species would be if you allow anything to eat as much food as it wants, no matter what it is, a person, a cat, a scorpion, a cell of yeast, it's not ideal for your health. It actually, as opposed to limiting it as long as you're not, starving. That when you cut back a little bit, when you calorically restrict, it's helpful for your health. Because if you allow creatures who are going to just send out signals, they're going to maximize their signal production, they're going to cut down their chromosomes, then their life wave system is not as precisely being redirected. And I think when you do that, you open yourself up to different diseases, different problems, and in particular cancer. I think that with this theory, cancer needs to be rethought, because you have this different avenue of life now. We look at cancer like, your life, like your body, it's just messing up. It didn't replicate some DNA, so obviously if it doesn't replicate DNA, this cancerous tumor body metastasizing takeover is the likely outcome. And I think that's uh, kind of silly. I think that cancer is doing a lot of things that are sophisticated. You know, there's angiogenesis, where it's redirecting blood into the tumor, right? It grows, it ramps up its metabolism, slashes the telomere count down. So what does that mean? If a tumor slashes your telomere count down, like, why would it do that, right? Why would it ramp up its metabolism? Well, maybe the purpose of a tumor is to make as many tumor life waves, right? So it takes over your body, it takes a part of your body, redirects it into building a tumor. And that's a major problem for life. There's no good way about that other than to just die at a certain age. You know, life is not always, its goal is not always to live as long as it can, because the longer you live, the more likely you are to have other life waves absorb into you, you know, potentially causing cancer or growth. It doesn't always have to be a metastasizing cancer. And then these things are just going to kind of pump out their influence. So let's say there's a lot of mice. There's this one type of mouse, and there's, I don't know how many in the universe. It could be trillions of mice. You know, from the perspective of a mouse in evolution, there's no reason for a creature to, you know, die. It might make sense for something to die or have a certain lifespan if the amount of waves that it's pumping out is more hazardous to the health of the, you know, your entire, you almost need a different word here, your specific species, you know, the mice that would be the same as, say, like two identical twins are the same. The best thing in that regard is to have a certain set lifespan. And I think we see this. It's, you know, when you look at lifespan of people, I want to make sure I don't like remember it wrong, but I think it's 30% of people make it to 90, and then it's like 2 out of 10,000 people make it to 100 from there. So, you know, that's like virtually everybody can't make it to 100, and I think that's kind of part of the plan. Like, your body doesn't want to live forever because it isn't about living forever. It's about creating an optimal life wave system. So we can see a lot of these things, and you can see things across cancer that really make it look like a very, very thought out, practical species. Like, you know, when you think about all the things that cancer does, like take metastasis, for instance, or just what parts of your body get cancer versus other parts. You know, have you ever heard of somebody getting heart cancer, for instance? Like, you know, no, right? Like, versus, say, lung cancer, and the reason I would think that heart cancer is extremely rare, like some people have argued that it doesn't exist, is that you can't grow a very big tumor in something sensitive like a pumping heart, because if you mess things up there, you're going to die. But if you have something like in your lungs, maybe it's just impeding your breath a little bit, you know, or, you know, a bigger organ, then you could have bigger tumors. So tumors don't want to kill you. It's just sort of this interesting dynamic that sort of develops. Like, tumors don't want you to die. Your body wants you to die at a certain age. It's kind of counterintuitive, but I think that's the way cancer works, and say metastasis too. I think, like, there's these signals that cancer uses. So, like, let's say you get cancer in your liver, right? And it's metastasizing. they found that you can have signals, that there's signals that tumor cells will send to other tumor cells, depending on the strength of the signal, will change where the rate of growth or the rate of metastasis. And I think the purpose of this, of metastasis, is so that you're spreading the load around your body. It would be better to have cancer in all the different parts of your body so you don't have, say, a specific organ failure leading to death. We can see that. We can see that under that guise, cancer then suddenly seems like it's being practical. I think that's the way that it works here. Your body can also has multiple ways of communicating things. So there's other things maybe your body could communicate as well, and I think it does. It could use the same system to, say, be used as an advantage in your mind or your immune system. You know, it could be the case that your body doesn't need to figure out an antibody for every disease through, some type of immune system every time. It could be the case that your body simply has a way of identifying different antigens, cross-referencing to see if there's antibodies in any of the life that it's communicating with, and try to fight disease that way. And I think that is the way that it works, which could lead to the prediction that I've learned that, there's differences in the genomes from like antibody to antibody when that antibody is designed to attack a different antigen. That there's tens of thousands of different genomes corresponding to all these different arrays of antigens. And like what I'm saying is that, one, the fact that there are these different genomes is a tip-off that it is using this type of system, because the assumption would be the way that it learned that antibody in the first place was by absorbing life waves from other antibodies and then using those antibodies, then using that life wave to create new antibodies. And then those antibodies, if they're successful, are going to be replicated in your body, right? So if your body then replicates these antibodies, and they're successful, your body's going to keep them around, then they have the freedom to create more of that specific antibody that was successful, in which case other creatures can then pick it up. So the immune systems can be shared amongst species, maybe even. I'm not exactly sure if it's if it's people sharing everything. I think there could be this sort of network of immune system function. The interesting thing about that, even more interesting, is your body, I believe, is doing the same thing, or mankind as you would, in the brain. That if you have a certain idea, if you have a thought, I think that your mind, probably more in your youth than as you age, but it's, you always do this, could be picking up different signals from other neurons. If you're thinking about, say, addition, maybe you're more likely to create something that is associated with subtraction. Maybe if you are, say, inventing a theory like this, just by focusing on it, by thinking about more of these things and making it your, stated life goal, which I have, you can kind of train your subconscious to sort of pick these things up so you don't really get stuck. So with this interpretation, what I'm saying is, like, with learning no matter what you're learning, the reason your body can be so flexible, so versatile, is because we are crowd sharing this information amongst all of the thinkers. So, say someone like Einstein, he doesn't necessarily have to like logically think out relativity. He just has to be very good, or relativity just has to exist somewhere in the whole universe. Maybe there's civilizations that are way ahead of us and they're teaching relativity in college like us. And then he's just sort of naturally sensitive to that by just randomly thinking about those things. Maybe his body's interpreting the discovery of relativity as, like a student who's trying to learn it. Same with calculus and math and language. And I think that that's the way that the mind works, which is a really, really powerful thing if you think about it, because it means, like, what I'm saying is you could potentially learn anything anyone in the universe knows, not like a specific person, but like what groups of people know, and ultimately learn like anything and pick up whatever is successful. It doesn't mean that it's right? It just means that it's popular. And I think that's a big difference, or maybe the big difference between, say, the intelligence of a person versus a whale. A whale has way more resources to grow a big brain, and they do have bigger brains than people. But, whales, they're big flippers. They can't, they don't have opposable thumbs and vocal cords like normal. They couldn't really become, say, like a spacefaring civilization. Mankind, on the other hand, totally could. Just because, like, from our vocal cords, our versatility. And I think that it could be the case that even if a brain is the same amongst animals, that doesn't mean that those animals are going to be, say, is smart in terms of things like, calculus, smart like building rocket ships, unless it makes sense for the group of those creatures. So I think that the niche of people is that in our brains is how we collaborate this information with each other, and just physiologically. Like, we are physiologically the most capable creatures to grow into, say, outer space, grow really big. The guiding hand of our instinct is not cavemen, right? It's whatever is the most successful in the universe. A caveman society, a hunter-gatherer, they can't really support a very big population without our modern technology. Whereas it could be conceivable that there could be a spacefaring civilization that has, with ships and automation, and maybe like Dyson sphere, if you know a little sci-fi, could have a trillion people. So if that's the case, you realize that what we naturally think is more geared towards a civilization that is really big, right? Successful in the terms of, numbers. And that really creates a much different viewpoint of where mankind's going. I think that it's a rite of passage, maybe, for older people to like look at the past and be like, hey, like, based upon this past, like, we're all doomed now. This new generation is gonna, like, with this, they're gonna destroy the whole world. They're gonna, like, we have nuclear weapons. We're just gonna everyone's just gonna blow everything up. We're gonna, like, because of the way war was before. And it never really works out like that, because civilizations that decide they're going to, that nuke each other to death don't exist, right? Because they're dead now, right? Civilizations that didn't nuke each other, maybe they're nicer to each other, maybe they've got some kind of compassion. They treat each other better, they work together better, they have natural instincts for civilization that make sense, that don't run into dead ends. They survive. And because of that, I think that the nature of civilization is to grow, probably to become more prosperous than we are now, to become bigger. And even though, based upon our past, it seems like everything's coming to an end, it's like never really plays out that way for thousands of years. And that's really maybe a sense for optimism. I'd love to see, the people's response, maybe what they think. It's a little difficult to just talk everything out all at once versus, to have specific conversations. I've had so many conversations with people over this, and I know, like, people go all kinds of different directions, and I think maybe one of the reasons that it's so positive, or why they get a lot out of it, is because I can, if I'm talking to someone face to face, I can listen to what they're saying, figure out whatever it is they think about evolution, which now I kind of look at is this major ad hoc theory, and just, change them. I mean, in the end of the day, I'm really just saying, hey, I think it's physically possible that life could be sending signals, and it's also more efficient. So why the hell doesn't it do it? But what I love to do is, I know there's these hardened STEM majors, this cancer researcher who's got, specific viewpoints, which I've run into before. So, write on the comment sections, this guy's a flippin' idiot, he obviously doesn't know about whatever. He doesn't know what RNA is. He don't, whatever it is you got to say. This guy, photons are fundamental particles. What does he know? Put it in there. Whatever questions you have, write them out there, and I'll make another video of it. I'll put more of the physics stuff, maybe create some visuals. I'm curious to see, with the power of the internet, what are the things people are most likely to think? And I'll respond. I'll make more videos. Just let me know. Thanks.